Okay, so from last time, we are studying the subspace, right? So just to remind you of what the subspace is, it's basically a subset of the vector given in a fixed dimensional space, but they have to be, they have to satisfy the condition that they have to be closed under the linear combination of these vectors, right? And then we discussed about the set of vectors which are called a basis given a subspace, and those bases should fully span the given subspace, and at the same time those vectors should be linearly independent, so we don't allow any redundancies, right? And from that fact, suppose we pick up any particular point in our subspace, because the subspace is basically a subset of the vectors, and so we can choose one of these vectors in our subspace. And then we should be able to always represent that particular vector as a linear combination of our basis vectors. And that linear combination representation is always unique because those basis vectors are always linearly independent, right? Okay, and then so I'm not sure if we discussed about these subspace related to a given matrix, but suppose we are given just an arbitrary size of a matrix, for example, like 4 by 3. Okay, so suppose we are given, did I say 4 by 3, right? So suppose we are given this size of a matrix, and then we are basically given 3 columns, right? And then we can think of the span of these 3 columns, and that span is actually the subspace, right? So that is called the column space of an A, and that is part of R4, right? But in this case, even though that column space of an A is spanned by these 3 vectors, but they may or may not be linearly independent, right? So when talking about the basis of these of this subspace of this column space of an A, and then we have to choose only the linearly independent vectors, right, among these 3 columns. So that is the basis of our column space. Then another subspace related to this matrix is called a null space, right? And given the same size of matrix of 4 by 3, and then in this case, this null space is basically all the possible solution of our homogeneous linear system of having zeros on the right hand side, right? So in this case, we basically collect all the possible solutions of this AX equals 0. So that is called a null space. And then we proved that this null space, which is the collection of all the possible solutions of this homogeneous linear system, this set is basically satisfying the condition or requirement of the subspace, which is being closed under the linear combination. But here, let me point out that this subspace, called the null space of matrix A, is part of R3, right? So in the case of column space, it is part of R4, but null space is part of R3. Okay. Okay. Then let's look at some examples related to this column space and maybe null space. And given this matrix, so the question is, yeah, we have to find the basis or set of vectors of our null space of this given matrix. Okay, so the null space is basically a subspace, and I mentioned that the subspace is always represented as the span of some vectors, right? But by the definition of the null space, it is just defined as all the possible solutions of that particular homogeneous linear system, right? So, yeah, although we proved that this satisfies the condition of being closed under the linear combination, but we didn't know, yeah, we haven't studied yet how to find the particular basis vectors of this given null space, right? So we will study how to obtain those basis vectors that will span this null space. Okay. So this matrix is converted into this form of reduced echelon form. Okay, this reduced echelon form. And the basis of our null space is basically related to the parametric vector form that we studied, okay, in chapter 1. So in this case, our general solution or parametric vector form is obtained by representing the basic variable in terms of free variable, right? So here we have a pivot, over here, only the 2, and then these are the basic variables, right? And then all the others are the free variable, and then we basically represent this basic variable as a free variable, right? x1 is represented as these variables, right? So we obtain this, and then another basic variable, which is x3, which is this guy. So this is a basic variable, and then x3 is represented by these 2, right, which are corresponding to x4 and 5, right? And then what about the free variable when forming this parametric vector form? We just represent it as as itself, right? Because we have no additional representation for our free variable. And then this representation is always factored into this form where we have which are the linear combination of these vectors that we factor out with the associated coefficients corresponding to our free variable, right? Okay, and then suddenly, we can view it as a linear combination of some vectors in order to represent our null space, right? And then, so is it enough? So let me ask the question. So the question is whether it is enough to say these 3 vectors are the basis of our null space. So the basis should satisfy the linear independence, and also it should fully span the given subspace, right? And then from this representation, I mean the any vector included in our null space is represented by that form, right? So if we use these 3 vectors and then span, if we use the span of these 3 vectors, and then it will fully cover the entire entire subspace of this null space, right? Because any given vector in our null space is always represented by that, right? And then the other question is to check whether these 3 vectors are linearly independent or not, right? But let me say one thing here. So basically the basis vector is obtained by just representing your null space solution. I mean the solution for homogeneous linear system as that parametric vector form, and then these 3 vectors are always linearly independent. So it's always true. Okay. And then let's think about why. Okay, let's think about why. So you have to flexibly, you have to be able to flexibly think about this matrix horizontally or vertically. So in this case, let's focus on this entry. So these three entries, okay, these three entries are coming from the representation of our free variables, which are, let me use the color. So those guys, and then those guys are represented by themselves, right? And then when they are factored out, and then so we will always have these three linear combination coefficients, and then what is the corresponding value over here? So it is just 1, because we wanted to represent x2 as itself, and then when factoring, when considering it's a factored representation like this, and then it will be always multiplied with the x2, right? And thus this value will always be 1. But what about the other values? By that I mean those values, okay? So these values, so for example, let's think about this case. So it means we are representing x1 in terms of all the free variables that we have, right? So x2 and x4 and x5, right? So these 2 and 1 and -3 are just those corresponding coefficients with our free variable, right? But what about our each of our free variable? It has the representation of just itself, right? And then it will always have 1 over here, but 0 all the time, corresponding to the other free variables, right? Okay, and then the other entries corresponding to here is also the same, right? So this value is used to represent this x4 as just itself, which is just an x4, right? But when thinking of the other free variable of x2 and 5, like this guy and this guy, their value will be always 0, right? So if we think of, if we pick up our 3 of these free variables, okay, then let's just extract out the representation of x2, x4, x5, okay? So in this case, it is represented as x2 times 1, 0, 0. I mean, it's a really obvious one, but 0, 1, 0 and x5 and 0, 0, 1, right? And then, I mean, if we can do a little bit more elegantly, and then we can represent it as a matrix multiplication of this almost trivial equation of identity matrix times just some x2, 4, 5, okay? Okay, and in this case, let's think about whether these 3 columns or these 3 columns are linearly independent or dependent. So the columns of identity matrix are always linearly independent, right? So from the fact that, or from the patterns that we always find like this, which is that we always find 1 only in that that particular free variable itself, but all zeros for other free variables, okay? And then this kind of pattern will actually make these 3 columns always linearly independent. And even if they are part of this larger dimensional vectors, they are always also linearly independent, right? Okay, so you can have this kind of intuition, and also at the same time we can do we can prove this a little bit like mechanically, without not much of a spirit or the intuition. And let me show how. So in this case, in order to determine whether these three vectors are linearly independent or not, what should we do? We have to form the homogeneous linear system by using these three vectors, right? So we just collect these three vectors, and then what is our matrix A? It will be, yeah, this size of a matrix, because we have three columns which are all in the 5-dimensional space, right? And then we think of this homogeneous linear system like this, right? And then we have to determine whether we can find any non-trivial solution or not, right? And then in this case, so let's bring out, let's extract out the second row, and then that second row will form our second row in this matrix, right? And in this case, let's think about the original equation corresponding to this row. By that I mean, so it was x2, no, that x1, x2, x3 are different from these x2, 4, 5, right? So they came from the original matrix like this, right? And then these are the new vectors that we obtained by by representing or by obtaining this parametric vector form, right? And then we want to determine whether they are linearly independent or not. And then, okay, so let's just call it as a z1 and z2 and z3, because they are different variable from x1 through x5, right? And then from here, what is our equation over here? Times this. And then it will be just like z1 times 1 plus 0 times z2 and 0 times z3, and that should be 0, right? And that means z1 is 0, right? z1 is 0. And then similarly, let's think about this fourth equation, which has the coefficient of 0, 1, 0. And then in that case, we obtain that z2 is also 0. And z3 is also 0 by using the last equation, which has the coefficient of 0, 0, 1, right? And thus, we always obtain the conclusion that this vector, I mean each element in our vector, is always 0, right? Which means we have no other non-trivial solution, and thus these three vectors are always linearly independent. Okay, so all this, all the key, key observation is from here, right? We represent our free variable as itself without involving any other. Okay, so we now know how to obtain the null space and the basis of the null space, which is coming from just a parametric vector form. And once we obtain these vectors, and then they are always linearly independent. So you can just safely just write your answer as these three vectors as your basis for the null space. Now let's think about the basis for our column space, which is much easier. Okay, so in this particular example, we are given a matrix that is already in an reduced echelon form, because we have a pivots over here which are all ones, right? And then lower and upper entries are all zeros. So in this case, so when talking about the so here, you guys know that the column space is basically a span of these 5 columns, right? But we have to exclude out, or we have to remove linearly dependent column, right? So that way we can obtain our answer for the basis of the column space. And then from here, which variables or which columns are linearly dependent. Okay, so we have a basic and three free variables over here, right? Oh no, I didn't find the pivot over here. So we have a 3 pivots, right? And so B, B, F, F, B. Okay. So in this case, so when studying the linear independence, there were 2 different versions or 2 different ways of thinking of our linear independence or dependence. The first one was this kind of formal definition of checking whether this homogeneous linear system has at least one non-trivial solution or not, right? But in the other scenarios where we check the linear independence or dependence, we think of the scenario of adding one vector at a time in our set of vector that forms our span, and then check the next vector, check whether the next vector is included or that is inside of the span of the previous vectors, right? So if we can find at least one such vector, and then that's when these vectors are linearly dependent, right? Right? And that was how we determine the linear independence or dependence, from the intuitive process. But in this case, because we have a free variable, so it is clearly linearly dependent. But in this case, in the scenario of adding one vector at a time in the span set, okay? So which vector is included in the span of the previous vectors? So those vectors are the columns corresponding to the free variable, right? So in that case, the first vector and the second vector, which are up to these 2 vectors, they are linearly independent. But the third vector, which is our free variable, is actually included or is inside of the span of the previous 2 vectors, right? And so if we think of this, if we want to obtain only those vectors that are linearly independent while excluding the linearly dependent vectors, and then so our job is to just bring out those columns corresponding to our basic variable. Okay? And then from here, so I had to remind myself about what we discussed over here. So it was in the linear independence or dependence. So it is a little bit more complicated form, complicated example where it's a little dirty, but we can find the pivot over here in the first column and another pivot in the third column, right? And then in this case, I mentioned that we can represent the column in our free variable, okay, column corresponding to the free variable as the linear combination of the previous vectors, right? So that way, the column corresponding to the free variable is actually inside of the span of the previous variable. And then if that is the case, and then we should be able to find that linear combination representation of the previous vectors in order to represent that column corresponding to the free variable, right? So in this case, how did we find the linear combination representation of our free variable using the previous vectors? So for example, looking at these 2 columns of all 1, 0, 0, 0 and -2 and all zeros. So in that case, the second one is free variable because it doesn't have a pivot. And it means, we should be able to find out the representation, linear combination of only the first variable in order to represent the second variable or second column, right? So what was the representation over here? So do you guys remember this example or not? Okay, so let me, personally I think it is a little bit interesting and kind of important. And let me just use a little simpler example. So suppose sum of our matrix was something like this. Okay, and then this guy had a was converted into like okay. So we have 1 over here, and 2, and 0, and 0, and maybe 3, 4, and we have to have a, let's suppose this kind of case. Okay, suppose we obtained this kind of echelon form, right? And then from here, BF, right? And then let's try to represent the second vector. 저기 무슨 필터가 있어요? 렌즈도 아니고 필터를 바꿔라. 네. 아, 렌즈였어요? 중요한 건 아니니까. 네. Okay, so here we want to find out the representation of the second vector corresponding to our free variable, right? As the linear combination of the previous vector, right? And then what is the representation? Can we obtain that representation from this reduced echelon form, right? And then here the logic is as follows. Yeah, basically, why did we change it into this echelon form or reduced echelon form? Because they keep the solution remain the same, right? So the solution will be the same, right? So what is the solution? The meaning of the solution? Yeah, solution is corresponding to this linear combination coefficient, right? To make zero vector. I mean, we talk about the homogeneous linear system when talking about this linear independence or dependence, right? And so here, if we can find the solution that satisfies this, I mean, as a non-trivial one, and then that is the linear dependence case. But more fundamentally, the solution that satisfies this equation will be the same as the solution that will satisfy this equation. Okay, right? And so here, let's view the solution of this homogeneous linear system, which uses our reduced echelon form in order to obtain the linear combination representation of this second column in terms of the previous columns, right? Because that is corresponding to like adding one vector at a time and then representing the column corresponding to the free variable as the linear combination of the previous vectors, right? And so we want to obtain something like this, V2 as some V1, because this is the only one previous vector that we have, right? And so here we can change it into this form, minus C1 V1. So this is all what we studied already, but it's just a review. So this is something like this, right? And so suddenly we can view it as a kind of a linear combination of given vectors in order to make zero vector. And then where are V3 and V4? Because we have 4 different columns. I mean, we can simply set them, set their linear combination coefficient as zeros, right? So, 0, 0, and 1 here, right? And so in this case, what is our column corresponding to V1 and V2? So these columns are these guys, right? Because that is our linear, homogeneous linear system, like, this one as C, C times X equals 0, right? And then the V1 and V2s are like the columns in our matrix C. And then these columns are these columns, right? And then, so here, we want to represent this column as a linear combination of this column. And how can we obtain that? So we can represent this guy in terms of this guy, so that their sum or linear combination to 2 becomes 0, right? Because we have to obtain a 0 vector, right? And so what is our case? So we can just multiply negative 2 here, right? And then, yeah, they are canceling out with each other, and then we will obtain 0. And then, yeah. And then from the structure of a reduced echelon form, these values are all 0. So, yeah, for whatever linear combination of these, and then they will just remain as 0, right? So those are, yeah. So C1 is just 2, right? So that is our non-trivial solution, okay? And also that is our particular linear combination representation of the second vector in terms of the previous vector. Okay, and then we have another free variable, which is this guy. And then it means that the fourth column is should be able to be represented as the previous vectors, right? And then what is the representation? In order to represent that fourth vector as a linear combination of the previous ones, right? And in this case, we don't even need to use the previous free variable, right? And then we can, yeah, it is just enough to use only the basic variable, I mean, that was found previously, right? So in that case, yeah, let's try to reconstruct this linear combination representation using the previous vectors in order to represent the fourth vectors, I mean, the last vector. Yeah, so, similar to these kind of, how we obtain this coefficient. So let's set it as 1 over here. Right? Because that way we can obtain like V4 as a linear combination of like V1, V2, and V3. And here we don't even use V2, which are the previous free variable, right? And then, yeah, this coefficient will be 0. And then how can we obtain these values? So that can be obtained really simply because this value is just 3 times, right? And then from the structure of this reduced echelon form, these are all zeros, right? So we can just simply make or adjust this value so that we can cancel this value out, right? And so the value will be negative 3, right? And then what is the value over here? Yeah, negative 4, right? Okay, so this one is our another solution, I mean another non-trivial solution of our homogeneous linear system, right? So again, the point is that the columns corresponding to the free variable is always represented as a linear combination of the previous vectors, right? And that means, I mean, why do we need this kind of effect? We want to be able to select only those linearly independent vectors, right, from our columns in the given matrix, right? So here, so yeah, we can just simply extract out or select only the columns corresponding to the basic variable. So that will be your basis for the column space, okay? And again, they are linearly independent, and then still fully span the column space of an A, right? So in other words, the span of the 5 vectors, all the 5 vectors, is the same as the span of those 3, only the 3 columns corresponding to the basic variable. Any questions? Okay, and then the solution shown in these slides are just about how we obtain these linear combination representations. Okay, so let's move on to another example. So this was kind of a special case where fortunately we are given the matrix that is already reduced echelon form, but in general we will be given like this kind of matrix. And then in order to determine whether, which variables are or which columns are linearly independent one, which cannot be represented as a linear combination of the previous ones, okay? And then what we have to do is just to simply change it into reduced echelon form. And then in this example, I mean, intentionally the author actually made this matrix to have the same reduced echelon form as the previous matrix. Okay, I mean, so once you do the row reduction on this matrix, and then you will obtain this exact same reduced echelon form. Okay, and then from here, so we obtained, I mean, we figured out which variables are free variable and the basic variable. So B, B, F, F, B, right? So we can just annotate these variables like this, okay? And then what is the basis of our column space? We can just simply select these three columns, right? That will be your basis, right? And then in this example, I mean, the intent of making this the reduced echelon form of this matrix the same as the previous one is that, I mean, yes, the author emphasizes that you shouldn't be confused, against picking up, like, so you shouldn't pick up the columns from this reduced echelon form. Okay, I mean, so in this example, okay, what is our basis of our column space? Okay, so we have two basic variables, right? And then where should we pick up our two columns? Is it from here or is it from here? I mean, in this case, if we pick up the columns from here, and then it will be 1, 5, 9 and 3, 7, 11, right? Because these are two basic variables, right? But if we pick up the columns over here, and then what is our columns? It will be 1, 0, 0, which has the pivot, and then also 0, 1, 0, right? So which one is the correct answer? I mean, as the basis of our column space. The left or right? The left, right? The left. Right? I mean, our column space is basically a span of these four vectors, but not these the four vectors on the right, right? So we have to select those columns from the left or the original matrix. So the point is that the reduced echelon form is only used to figure out which are the basic variables, okay? But the actual selection of these columns for our basis should be done from the left matrix, okay? Okay, and then we can also make sure or verify this kind of a simple kind of fact from this perspective. So yeah, in this case, these column space, I mean the column space of these four vectors, I mean even before we talk about the basis, which are only the linear independence, I mean let's just think about the linear combination of these four columns, okay? And then if we look at the last entry, 9, 10, 11, oh, maybe 12, or yeah, 11 will be fine too, but the linear combination of these four vectors will have some non-zero value on the last entry. So if we think of the linear combination of these four vectors, and then it will have the three-dimensional vectors, and this value will have non-zero, right? Because we have non-zero values of 9, 10, 11, 12, right, in the original matrix. But if we think of the span of these four columns, which are from the reduced echelon form, and then let's focus on the last entry. So they are all zeros. So yeah, so in that case, the linear combination of these columns will always have zeros at the last entry, right? So it is not a correct answer. Okay, so the left one is the right one. Okay. So this warning is about what I just described. Okay, and I think that's it for this chapter 2.8. Any questions? Okay, then let's move on to chapter 2.9. So probably most of the parts in this chapter 2.9 was explained probably in the last class. Okay, so we studied, or we know the definition of this dimension, right? So what is the dimension? It's the number of basis vector of a given subspace, which are the count or the number of only the linearly independent vectors that spans our subspace, right? And then what is the rank? So let me just jump straight in to the rank, the definition of this rank. So rank is simply the dimension of the column space of an A. So we just consider, given a matrix A, we consider the column space of an A, and then we consider the dimension of this column space. And then, so that corresponds to the number of basis vectors to form our column space of an A. And as we saw in the previous example of like a free variable and basic variable and so on. Let's see. So what is the rank in this case? In this case, rank is, by definition, the rank is the dimension of some certain, the column space, right? And then the number of basis vector of our column space, which are just 2, and these 2 is the number of basic variables, right? So basically, the number of basic variables are your the rank of your matrix. Okay, so that is the definition of this matrix. The definition of the rank of a given matrix. And that rank, so rank is basically the number of the linearly independent vectors out of the entire columns that you have in the matrix, right? And then if you remember, if you remember the discussion about the sum of rank 1 outer product in order to represent a matrix multiplication. So we have some matrix over here, and then so let's suppose the matrix is like 10 and maybe 35, and then suppose this matrix can be so we have 35 columns, right? 35 columns, and out of these 35 columns, suppose we have a basic variable, only maybe 7 basic variable, only the 7, okay? And then it means only the 7 linearly independent vectors are existing in here, in these 35 columns. And what does that mean? It means we can represent all those columns that we have, like 35 columns. Each of our 35 columns should be able to be represented as a linear combination of only the 7 columns, right? 7 column vectors, right? So so that is actually the kind of a physical or intuitive meaning of a column. So even if we are given really large matrix, but some hidden really linearly independent vectors may be just a small number out of these so many number of columns that we are given. Okay, so in order to the finding out only those meaningful kind of components or meaningful column vectors, by that I mean just the linearly independent vectors. Okay, So finding those linearly independent vectors plays a kind of important role in data analysis and things like that. Okay, so that was the rank of the matrix. And then back to the first slide in this chapter. So we discuss, we study about the notion of the coordinates in this chapter. Okay, so coordinates of an x relative to the basis beta. Okay, so initially the situation is we are given a subspace. Okay, maybe that subspace is maybe plane out of this three-dimensional space. Okay, so plane is a subspace, right, in the three-dimensional space. Okay, so suppose we are given that subspace, and then we pick up one point from that subspace. Okay, and then as we discussed in the previous chapter, we should be able to find unique linear combination representation of that point. Okay, of that point with respect to a given basis vector of that subspace, right? So suppose we are given this subspace like this plane, and then suppose you found like a set of basis vectors. So maybe these two vectors can be your basis vector, right? And then suppose you are given one particular vector inside of our subspace, right? And then we want to obtain the linear combination representation of that point. Okay, that point. And then the linear combination coefficient is called the coordinate of that vector with respect to our basis vector. Okay, so what does that mean? So the intuitive meaning of that is as follows. So suppose, let's think about the span of maybe 1, 2, 3, and 4, 5, 6. So this one clearly forms the plane, and these two vectors will be the basis vector because they are linearly independent, right? Okay, and then I'm gonna give you one point. -2, -1, and 0. Okay, and then we want to obtain the linear combination representation of that point. I mean, we didn't even check whether this point is inside of the span, right? But we will do the row reduction and check whether that is inside of the span, or in other words, we will check whether the solution is existing or not by checking the column. I mean, the pivot is existing in the rightmost column, right? So you know how to do that, right? And let me give the solution directly. I mean, by skipping those tedious row reduction process. And that solution is like this, okay? Because I just created this vector of -2, -1, and 0 just in mind, I mean, of these linear combination coefficient, okay? Okay, and here in this case, 2 and -1, okay? This 2 and -1 is the coordinate vector, okay? Coordinate vector of this vector with respect to these two basis vectors, okay? And then, let me give a little bit more intuitive kind of figure in order to properly understand this. So it is something like this. So we are given these two-dimensional subspace, right? And then we have two basis vectors, right? And then we can just bring this plane. Suppose, let's just imagine. Maybe we may have the figure like this, okay? In this case, we can think of this this plane, and our basis vector is these two vectors. And then suppose we are given one point over here. It is like -2, -1, and 0 in the previous example. And this one is 1, 2, 3, and this one is 4, 5, 6. Okay, and then what is the linear combination representation of this point with respect to our basis vectors? That is 2 and 3, right? That is 2 and 3. And this 2 and 3 is the coordinate vector of this vector, okay, with respect to our basis vector, okay? And then the intuitive meaning of this is as follows. So you see this kind of a slanted grid, okay? By that I mean these grids, okay? These will actually work as your kind of regular grid, okay? So what is the coordinate like this? Or, yeah, let's think of just really regular coordinate system. Like, so we have two axes of an x and y axis, and then 1, 2, 3, 4, 5, and 1, 2, 3, and so on, right? And then we just simply draw these grids over here. Okay. Now what is the coordinate of this guy? This guy is 2, 2. It's a really easy one. And what about this guy? What is the coordinate of this guy? 3, 1, right? And here it is almost the same as this figure. So in this case, this two-dimensional plane is actually embedded in a higher dimensional space because they are existing in the three-dimensional space, right? But still, we can just like we can tear it out. So we just cut them out, and then we bring this really thin two-dimensional plane, okay, into and put it into some three-dimensional space, or maybe in a higher dimensional space. We can do that, right? And then here we can think of this really simplest standard basis vector, right? So in this case, our basis can be viewed as 1, 0 and 0, 1, and then you guys know that this guy 3, 1 is represented as the linear combination of those two standard basis vectors, right? And then we can think of this 3, 1, which is really the coordinate values that we already know, as the linear combination coefficient coming from this linear combination representation of the given vector by using a particular basis vector that we have, okay? And then yeah, from this analogy, or from this this kind of process, we can, yeah, we bring that into higher dimensional space and embed it into this higher dimensional space. And then also our basis vector can be a little bit, yeah, more complex, which means that the length can be more than or less than 1. I mean, it may not be 1, and also their angle may not be a right angle or the 90 degrees. So that is, I mean, that corresponds to this blue figure. So in this case, so this is a okay. So this vector 1, 0, okay, 1, 0 is actually kind of transformed into this V1, which is 1, 2, 3, okay, and then this 0, 1 has actually moved into this V2 of 4, 5, 6, okay. That's what I mean by embedding this two-dimensional space into three-dimensional space, right? And then where is this point moved? Okay, 3, 1. It will be over here, right? So this kind of grid is still available over here, and this line is corresponding to this line, okay, and then this line is corresponding to this line, and so on, right? So it's like this kind of grid has actually changed it into like this thing. So we have origin here, and then maybe this, okay. So this one is V1 and this one is V2, and then when thinking about the coordinate of this point, and then it can still be thought of as 2, 1, right? So it's really the coordinates, okay? coordinate, 한글로 coordinate이 뭐죠? 좌표, 그렇죠? 좌표 값이라는 뜻이에요. 좌표 값. 네. 다만 이제 베이시스를, 네, 하여튼 주어진 어떤 특정한 베이시스. 그리고 좌표 값은 이제 2차원 벡터의 좌표 값은 당연히 두 개가 나와야 되잖아요. 그죠? 근데 여기서는 아까 얘기했던 뭐 내가 인베딩을 한다는 이야기가, 네, 어떤 하이퍼플레인이 2차원이면 뭐 그거의 베이시스 벡터는 두 개가 있겠죠. 근데 중요한 건 저기 플레인, 네, 그냥 이 평면의 디멘전이 2차원이다. 혹은 베이시스 벡터가 두 개다. 뭐 두 개의 리니얼리 인디펜던트한 벡터에 의해서 스팬이 되니까. 근데 그 सब스페이스는 기본적으로 뭐 3차 혹은 4차, 5차에서 존재할 수 있는 거예요. 그죠? 그러면 거기서의 그 두 개의 베이시스 벡터 자체는 뭐 3차, 4차, 5차 벡터가 되겠죠. 5차원 벡터가 되겠죠. 이것처럼 1, 2, 3, 4, 5, 6. 얘네가 일단 2차원, 그러니까 베이시스 벡터를 두 개짜리인 그런 सब스페이스지만 얘네들은 기본적으로 3차원에 살고 있는 애들이잖아요. 네. 그러니까 베이시스 벡터 자체는 3차원으로 표시가 되지만, 네, 이 सब스페이스에서 한 점을 뽑았을 때 걔의 어떤 조금 뭔가, 네, 새로운 형태의 좌표값, 그리고 그 좌표값은 뭐냐? 바로 우리의 그 주어진 그 베이시스 벡터, 그리고 그걸 가지고 저런 평행사변형을 쭉쭉 만들어 갖고 이렇게 그 모는 종이를 혹은 그리드를 만들었을 때 그 포인트, 그 좌표값은, 네, 실제로 우리 베이시스 벡터 개수만큼에 해당하는, 네, 그 디멘전을 가지는 좌표값으로 나타낼 수 있다는 거예요. 네. 그게 여기서 얘기하는 coordinate, 네, coordinate with respect to the basis vector. 그러니까 우리한테 주어진 베이시스 벡터에 대한 좌표값이다 라는 뜻이 돼요. 그리고 그거는 뭐 그냥 단순하게, 그러니까 뭐 이런 직관적인 의미가 뭐 그냥 흥미로우니까 좀 더 이야기를 해주는 거고, 기계적으로는 저 좌표값은 그냥 주어진 베이시스 벡터를 가지고, 네, 어떤 한 점이 주어졌을 때 걔를 리니어 커뮤니케이션을 표현하고 걔에 대해서의 어떤 리니어 커뮤니케이션 코에피션트가 이제 여기서 부르는 그 새로운 그 좌표값. 근데 그 좌표값은 바로 주어진 이 베이시스 벡터에 대한 좌표값. 그래서 이제 with respect to given basis vector라고 이야기를 하는 거예요. Okay, so yeah. Personally, I think this kind of intuitive understanding is more interesting and important. But really, those examples are, just, yeah. These are, yeah. These don't have much special things. So we are given this three-dimensional vector, which is inside of the subspace spanned by these two basis vectors. Okay. Okay, and then we can just simply, in order to obtain the coordinate vector of this vector x with respect to our basis vectors, okay, we can just construct this linear system, and then just to solve for these C1 and C2. Okay, so that's it. And C1 and C2 is your coordinate vector. Okay. Okay, and that has a kind of special kind of notations. The coordinate vector with respect to a given basis, and that basis is called this kind of curly b, and this vector x, yeah, and this one. So here, okay. So 3, 12, 12, 7, this vector, and b, yeah, some weird b, will be, what is the answer? Okay, 2 and 3, okay. So, yeah, you can understand the meaning of this notation. Okay, and then the next slide is talking about this isomorphism. Isomorphism. Yeah, so I don't have, honestly, I don't have much insights about what this means, but it's talking about some mapping from mapping Where is it? Okay, yeah. Okay, so we can think of the mapping from that figure on the left into a embedded subspace. I mean, two-dimensional subspace embedded into higher dimensional space, right? So we can kind of morph or transform or distort just a regular and the standard coordinate system originally in the two-dimensional space, like this figure, okay? And then we can transform it into the figure on the right, okay? And then can we go back from the right to the left? In other words, is it a one-to-one mapping? Is it a one-to-one mapping? So what I mean by that is, so we thought about this point, right? And this point is mapped over here. And can we go back from this point into here? In other words, is this point mapped by only one unique point from the left figure, or are multiple points mapped into the same point? It's always one-to-one mapping, right? And why is it one-to-one? Why is it one-to-one? It is because our basis vector are linearly independent, right? Yeah, linearly independent will give only one solution. So here the mapping can be found like this. So if we think of this guy, let's see, where is it? Okay. So in this kind of example, we can think of the mapping from, what is the original? Yeah, 312 and 7 into 2, 3. Okay. And this vector, okay, this vector is something like this point, right? And then that point is actually corresponding to this vector in just a standard two-dimensional space, okay? And then the question is whether the mapping between these two vectors unique, I mean one-to-one or not. In other words, yeah, from this linear system, yeah, this vector has a unique representation in terms of this linear combination coefficient, or will it have many possible solutions? I mean, it's clearly not the case because our basis vectors, by definition, are linearly independent. Okay, so yeah, we can move from one space to the other, and also we can, yeah, do the inverse mapping from that into the original space with no problem because it's just the invariable mapping or one-to-one kind of mapping. Okay. Okay, so this one is oops. Yeah, this blog is quite a helpful blog if you're interested in studying maybe deep learning. And then yeah, this is a personal blog of a particular guy whose name is Christoph Ola, yeah, who works now at the Google Brain, and yeah, he spends a lot of time on explaining really complicated notions or concepts or techniques in really kind of intuitive manners with a lot of figures and animations and things like that. So yeah, so there are a bunch of interesting articles, and among them there is a kind of figure like this. Okay, although this one is showing, yeah, although this one is showing some transformation made in a particular one single neural network layer, okay, in the fully connected layer. And in this case, yeah, you can also think of this as a kind of coordinate system changes. Okay, so if we, yeah, in the previous example, in this case, so we think of the I mean, which one is the original one and which one is transformed one? I mean, it can be like, yeah, it doesn't really matter. But we can think of transforming one space to the other, and then transforming another space to the original one, right? And then here, let's think about the transformation between the two-dimensional space. Okay, just the same space. Okay, so in that case, in the same space, so let's just think about our entire universe as just two-dimensional space. Okay, and then we can think of this grid coordinate system like this, right? So this is a 1, 0 and 0, 1, which we already saw in the left figure over here. Okay, and then the question is, so here we understand that the basis vector is not unique. Only the unique aspect is the number of basis vector, right? So the number of basis vector will be 2, corresponding to the entire universe of this two-dimensional space, right? And we can also think of our new basis vector like maybe this and maybe this. Okay, and then yeah, we can use these two new basis vector in order to represent any given point in our subspace, right? And then let's see. Maybe over here. So what is the coordinate with respect to the standard basis of 0, 1, 0 and 0, 1? So 3, 3, right? But if we are going to use this new basis vector, okay, and then what is the coordinate of this guy? It is like, and so you understand that, right? So what is the coordinate of this guy with respect to the new basis vector? What is the answer? 내가 좀 이상하게 그렸네요. 이래서 내가 미술 싫어했는데. Okay, now it makes more sense, right? What is the coordinate? 2, 1, right? Okay, so you can now understand this figure, right? So it is like, from here, we can think of this kind of mapping, yeah, similar to kind of linear transformation that we already studied. So it is actually transforming this standard basis vector of 1, 0 into this guy, okay? And then second standard basis vector of 0, 1 into this guy, okay? So our coordinate system has changed, right, into this parallelogram-like coordinate system, right? Still in the same dimensional space, right? And then additional kind of distortion like this, like convex, kind of a distortion is done by something called a nonlinear transformation or nonlinear unit called a sigmoid or 10H or things like that. But that is kind of out of scope of our class because that is actually nonlinear. But we are studying the linear algebra, right? But that's not really complicated. But it's just the additional kind of a simple post-processing, things like that. Okay. Okay. So this is the coordinate system. I mean the new coordinates with respect to this new basis vectors. Okay. And then this isomorphism is like the transformation, between these two, coordinate systems, one to the other, and that is also invariable mapping from the fact that our basis vector is always linearly independent. Okay, so it is saying this one-to-one mapping. And this slide is about the definition of the dimension of a subspace, but we already studied that because the definition of this dimension is simply the number of basis vector of a given subspace, and the notation is written like this. Okay, and yeah, we study the the dimension of the zero subspace. So our subspace, suppose our subspace contains only this zero vector, and then what is the dimension of the space? Once we add one non-trivial vector, and then so only vector that we can add is this zero vector, but once we add this zero vector, and then it is already a linearly dependent set, right? Because even using only one vector, we can obtain this non-trivial solution. So so we can set it as non-zero value, and thus we always obtain the non-trivial solution, and thus zero vector itself, the set of only one vector of this zero vector will be linearly dependent, right? And so it is not eligible for our basis vector because we have to only consider the linearly independent vectors, and thus this zero subspace is considered as having the dimension of zero dimension. Okay. Okay, so in terms of the rank, I already discussed, so in this echelon form, we have three basic variable or pivots, right? So here the dimension will be 3, which means, these three columns are only the linearly independent vectors to form or span our column space of an A. Okay, and then there is something called this rank theorem. So rank theorem. So okay, so the time's up, so let's stop here, and let's meet next Tuesday, and I believe the exam scores will be given or announced. You should be able to check your scores in the Blackboard in just a few days. Okay, so we will send an announcement, and also I plan to give out another homework, which is a kind of different types of homework, and in that homework you have to study some two online lecture, which is like 2.5 hours long, which is about the determinant. Okay, so I'll also send out the announcements about that. Okay, thank you very much.